Okay, welcome back. In this video we're up to set 3 out of the book, so we're going to be looking at extreme values. So that is where we have a whole lot of values in a data set, and there may be one value which is quite a bit larger or quite a bit smaller than most of the other values. So they're also known as outliers, that's what I've always called them. Anomalous values, rogue data. So there's different things we can call it. Extreme values or outliers is fine. Now the reason that these values could pop into our data, so it could be due to experimental mistake, and that is where the original way that the data is collected doesn't necessarily lend itself to collecting very good data that can be used. Poor sampling could be, sampling is talking about the people that we're actually asking or the places that we're getting the scores from. For example, poor sampling could be in the 100-metre sprint data. If we accidentally asked someone who was a marathon runner, then their time over 100 metres would be an outlier compared to the sprinters. A typographical error, that could be where the extreme value isn't actually an extreme value, but when it was recorded it was written down wrong, and so when the data is analysed, the incorrect value looks like an extreme value. And the other possibility is that the extreme value could actually be genuine data. So we have to be on the lookout for these values that are way outside of the rest of the range of the data. And so what to do if you recognise that there may be a extreme value. So if possible, recheck the data or do the survey experiment again. So that's try and recollect the data. You might find that yes, we rechecked and that outlier was an actual piece of data, or you might recheck it and realise, oh no, we made a typographical error, or for whatever reason, to identify if a piece of data is extreme. If it's not possible to recheck, because it really depends on the type of data collection, then you sort of need to understand the effect that extreme values can have on our calculated statistics. Okay, so that's sort of what we're going to be talking about in this example. So the first example in the book, where I'm not going to actually do, but as we get closer to you guys actually watching this video, hopefully online, I will set up a way that we can collect the data looking at everyone's age. So the idea is, and I'll just sort of summarise this, we want to find the mean, median, mode, range, interquartile range, and standard deviation of everyone in the class's age. So grade 11s could be 16 or 17 years old, some of the grade 12s might be 18. So we would sort of expect our mean, median, mode, quite a small range, to be around those values. And the idea is we want you to calculate all these things, and then we want you to recalculate, but also adding in my age. So that's your teacher. So I'm 44. So imagine we've got a huge data set with 16, 16, 16, 17, 17, 17, 17, 17, 17, 18, 18, 18, 18, and then we've got this one bit of data that's 44. So the idea is calculate all these things just with the students in the class and then recalculate them all by adding in this one extra bit of data, just to see how these things change. So by the time we get there, which should be sometime in term 2, hopefully I will have worked out a way for everyone to supply their data, everyone to have access to the data set, and then this will be able to be calculated. But in the meantime, let's just quickly summarise the effects of extreme values. Because of all our statistics that we can calculate, some will vary wildly, some won't change very much. So if we do have an outlier or extreme value in our data set, it can have a considerable effect on the range. So as an example with the age data, if my age wasn't included, we would have a gap between the youngest person, probably 16, and the oldest person, 18. So that range would be really small, probably 2. But as soon as you add in my age, 44, take away the smallest, then the range is a lot larger. An extreme value can have a significant effect on mean and standard deviation. So considerable, quite a large effect. Significant means it's sort of noticeable but probably not as huge an effect as on the range. But hopefully we'll see some examples where the mean, you will see how the mean changes when we have that one extra value. And finally, minimal or no effect on the median, mode, and interquartile range. And that's because, say we've got 16, 16, 17, 17, as that goes. So the median is going to be the thing in the middle, and if we have one extra value up here, all it really does is shift the median by half a step, because we've just got one extra bit of data. So the median isn't going to change very much. One extra bit of data isn't going to change the fact that we've got mostly people who are 17 years old. So that would be the mode. And because the extreme values are at the edges of the data, and the interquartile range is looking at the median of the top half and the median of the bottom half, this isn't going to change very much either, because one value up here, like we said with the median, it only shifts it half a space, half a position, so the interquartile range isn't going to be affected that much. Okay, so let's do this example, and when we're talking about this type of data analysis, this is what I would call a classic example. So this is V 3.1. Okay, so let's just try and draw this table. So this revolves around the salaries of different people working in a factory. Supervisor, manager, CEO, so that's the guy who owns the company. Salary, number, F times. So that's like frequency. So we've got workers, and so we'll just set this up and then I'll read through the question. 18,000. CEO, 300,000. So we've got 30 workers, 4 supervisors, 6 managers, and 1 CEO. Okay, so the question says, the CEO of a factory is proud to state that company employees are generously paid an average salary of over 31,000. So the CEO says workers paid over 31,000 on average. Let's just go A, B. But a worker in the factory claims that the CEO is being dishonest because he's one of the workers. In fact, employees are poorly paid. Find the mean, median and mode salary data. Who is right? How can you support the machine operator's claim? Okay, so first of all, let's find the mean, median and mode of this data. So we have a table, the F times column. So we're essentially going to say if we've got 30 people that earn 15,000, we're just going to multiply these to work out the total amount. I might need a bit slightly more space. The total amount paid to everyone, and then we'll add those up and divide by how many people are employed in total. So first of all, 30, 40, so we've got 41 people. And let's just very quickly calculate these. 15,000 times 30. 450 0 18,000 times 4. 72,000. 75,000 times 6. And one lot of 300,000. That's a 0, not a 6. So let's just add these up. Zeros, we've got 2. 5 and 5 is 10. 7 carry the 1. 4, 5, 9, 10, 11, 12. So the total amount spent on wages at this factory, 1,272,000 divided by 41 people. So the mean is 1, 2, 2, 2, 0, 0, 0 divided by 41, which equals 1, 2, 7, 2 divided by 41 equals $31,024.39. So, just based on that, the CEO said that workers are paid on average over $31,000. So we worked out the average, and yes, indeed they do, on average. So this number seems to back up what the CEO said. Okay, so now let's work out the median. So we've got 41 total people working at the factory. 41 plus 1 and 2. Half of 42 is the 21st bit of data. And looking at our frequencies, the first 30 bits of data, so the 21st bit of data is in here too, has a median salary. So the median is 15,000, which doesn't quite match that. Again, the mode is the one with the highest frequency. Straight away we can look at that and say, well, there's 30 people. So the mode is also 15,000. So, looking at what the worker said, the worker in the factory thinks that the CEO's claim is being dishonest. In fact, the employees are poorly paid. So, because these two numbers are together and the same, and they differ from this one quite a lot, that is an indication that maybe we have an extreme value. And essentially, because this one person, the CEO, is paid $300,000, which is about 2/3 of that, which is shared between 30 people, this CEO's salary is an extreme value in the whole data set, which is greatly affecting the mean. So when the CEO says on average, he's talking about the mean, not the median or mode. So how could you support the machine operator's claim? Basically, you would say that by including the CEO's salary in the calculations, it's pushing this mean much higher than it actually is when we look at the majority of people working in the factory. Okay, I hope that makes sense. So, now, let's get rid of that. We're going to look at how we can identify extreme values in our data. So, identifying. Okay, a piece of data can be identified if it either exceeds the upper quartile by more than 1.5 times the interquartile range, or if it's lower than the lower quartile by more than 1.5 times the interquartile range. That's a bit of a mouthful, but let's just summarize it in our data. So, out of a data set, we've got all the data in the middle. Our extreme values are going to be at the top end or the bottom end. And so this is a way to work out, based on how much data we have in the middle, how far out. It sort of works out an upper and lower limit. And if we have any data that's above the upper limit or below the lower limit, then we can call that an extreme value. So we've got Q1, and we're going to take away 1.5 times the interquartile range. So remember, the interquartile range was the difference between the 25th percentile and, well, Q1 and Q3. We multiply that by 1.5 and then we take it away from that lower quartile. So this is for the lower limit. Lower limit for extreme values. And then the upper limit is the third quartile, and then we're going to add this same thing, 1.5 times the interquartile range. So this is our 75th percentile, and we find the interquartile range, multiply it by 1.5, and then add it to that Q3. And then if we have any data that's bigger than this, we can call that an extreme value. Okay, so we have a quick example. This is going to be a very short video. So we've got some data. Let's just write this down. So this is V 3.2, 36, 38, 40, 37, 36, 42, 45, 42. Okay, so what we need to analyse this is we need the lower quartile, the upper quartile, and the interquartile range. So in order to get these, first of all, we need all the data in order. So I'm just going to rewrite it underneath from smallest to largest. Okay, so we've got a 35, we've got two 36s, 37, 38, what's next, 40, two 42s, 45 and 52. Because I've managed to line them up the same, we've got all the data. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 things. So to find Q1 and Q3, first we have to divide the data into two halves, essentially find the median. So we've got 10 bits of data, that's even, so it's going to be in between 5th and 6th, so our median is here. We don't really need that, but the average of 38 and 40 would be 39. Okay, so here's what we really need. So now we have a lower half with 5 members, 5 scores, and an upper half with 5 scores. So the middle score of the lower half is going to be this one. So that's Q1. And the middle score of the top half is that one, Q3. So we've got Q1 is 36, Q3 is 42, and the interquartile range is 42. Take away 36. Just re-recording this again, made a small calculation error the first time round. So we've got our data set, we've identified the quartiles, and the interquartile range is 42, take away 36, which is 6. And then we need to have a look and see if there's an outlier in the set. So first of all, we'll have a look at the bottom end of the set. So what we need to do is Q1 take away 1.5 times the interquartile range. So that is 36. Take away 1.5 times 6 is 9. So 36. Take away 9 is 27. And because our lowest value is greater than 27, then these are all well within our data range, and 35 is not an extreme value. All right, so we'll look at the top end now, and go Q3, and this time we add because we want to go, we're looking for an upper limit, 1.5 times the interquartile range. So we've got 42, that's 1.5 times 6, 42 plus 9, which equals 51. And if we look, our largest bit of data is 52. So because that's bigger than 51, we can say that this is an extreme value. So it's using these two little formulas, and in order to use them you need to work out the upper and lower quartile and the interquartile range, and it gives us a way to work out the upper and lower limits. Okay, I think that's where we'll leave this one.